Yesterday we looked at solving 2x2 systems. Today we're going to look at 3x3 systems and solve these by hand. 3x3, I mean it's 3 equations and 3 variables, x, y, and z. Now, it all depends on your strategy. Your strategy will dictate whether or not this problem takes you an entire page or 5 pages to work. So starting off is key. One good strategy is to look for an equation that has just 2 variables. Well, first looks pretty good, right? I have a y and a z. Second one, y, x, and z, so that's no good. And the third one, x equals a z. I think I might want to pick the one with the x, the variable equal. So this is going to be the first equation I'm going to use, because our whole goal here is to take a 3x3 and turn it into a 2x2. So like what we did yesterday. Because we can of course solve a 2x2, but not so much a 3x3, because this is talking about 3 dimensions. A little bit harder to see that in a graph that is only 2-dimensional. So now I have one equation that has only 2 variables, which means these other 2, I need to turn them into a variable that has just x and z. What do you think would be a good strategy to go about doing that? One of these needs to be a 2x2, or a 2 variable with only an x and a z. I have y equals negative 5x minus 4z minus 5, and a negative 2y plus 5z equals negative 3. This will be great here to use if only if it wasn't for that y. So what would you do? You don't know? Well, yesterday,
You put the x in the
keyword here is substitute.
You substitute the x or whatever.
Well, here's one equation with the y equals. So I'm going to grab all of this that y is equals to, and then do what? Substitute it in for this one. Now notice when I do that, I get x, z, z, and numbers, which is exactly what I want, just x and z. So let's go ahead and make that substitution. So negative 2 times negative 5x minus 4z minus 5. And then write the rest of this plus 5z minus, equals a negative 3. So far so good. I got one equation that's already good to go. It has x and a z. Another equation that I just need to go ahead and distribute and combine like terms. That'll have an x and a z only. So let's distribute. Negative 2 times negative 5x is a 10x. Negative 2 times negative 4z is a plus 8z. And then negative 2 times negative 5 is a plus 10 plus 5z equals negative 3. Let's combine our like terms. I have a 10x. I have 8z, and a 5z gives me 13z. And I'm going to go ahead and move that 10 over. So I'm going to subtract 10 on both sides. Negative 3 minus 10 gives me a negative 13. So this gives me an equation with just an x and a z, which I'm going to pair up to this equation with just an x and a z. So now this purple here leads us into what we did yesterday. A 2x2 system with 2 variables that I can solve using substitution. We could graph as well, but this is already good, set up and good to go, because I could take this value and do what? Substitute, yeah. Take this and bring it over here and plug it into that value, and that's going to give me one equation with just the z variable. So notice our strategy. A 3x3 that we want to turn into a 2x2 that I want to eventually turn into a 1x1. So this is going to give me 10 times x, but instead of x, I'm going to substitute 4z plus 4 plus 13z equals negative 13. Now I know this is a lot of work just for one variable, but you'll see once we get one variable, things will start cascading down and become a lot easier to find the others. So let's solve for this z. Let's substitute here, that's 40z times here, that's plus 40 plus 13z equals negative 13. Combining like terms, 53z. I'm going to go ahead and move this plus 40 over, so subtract 40. That's going to give me a negative 53 that you should be able to see requires just one more step. Divided by 53, and z equals
-1.
negative 1. So z equals negative 1. I found my first variable. Finally. I'll use yellow. My first variable right there. Z equals negative 1. What can I do with that to help me solve another variable?
Substitute
Where?
on X.
Yeah, very good. X equals 4z plus 4. Let me substitute it into here. Then I'll find x. So x equals 4z plus 4. X equals 4 times z, which is negative 1. And that's going to give me x equals negative 4 minus 4, plus 4, x equals 0. So the second variable was a lot easier to find than the first. Now I have two variables, x and z. How is this going to help me solve for y?
Plug both of them in.
Yeah, plug both of them in to this one. So I have y equals negative 5 times x, which I know to be 0 now, minus 4z, I know what z is, so minus 4 times negative 1, and minus 5. Now let's solve for y. So it equals 0 plus 4 minus 5, so therefore y equals negative 1. So x is 0, y is negative 1, and z is also negative 1. So I can again write these as coordinates, 0, negative 1, and negative 1. That is my final answer. Because if I were to graph these three equations in a three-dimensional graph, this is where they would intersect at that point there. So again, our strategy, take the 3 by 3, turn it into a 2 by 2, into a 1 by 1 to solve for one variable, use that variable to solve another variable, and use both of those to solve the remaining variable. That's how you solve 3 by 3 systems via substitution by hand. Now there is a method in the calculator, but we'll look at that a little bit later. Let's do one more, since these are kind of winded and they take forever. The whole point of this is your strategy. What would be the equation you want to use?
Top one.
The middle one.
The middle one.
The bottom one.
The bottom one? Okay.
Oh, wait.
Well,
I'll say the middle one.
Yeah, man.
the middle one has 3 variables.
No.
Oh, okay, no.
Remember, we want to turn the 3 by 3 into a 2 by 2. Which one's already good to go with the 2 by 2?
The top and
These two, which one do you think might be the easiest to work with?
The bottom one.
The bottom one?
Oh, no, the top one.
top one.
Top one has an x equals, right?
Yeah.
It's already got one variable ready. So we'll grab that one, which means I need to turn one of these equations into an x and a z. How can I pull that off? Again, we're going to need to do some substitution. What would you substitute?
The middle one.
The middle one into where?
The X. Oh, no. Oh my.
This is y equals, with all of this, what would I do with this y equals problem? Substitute it in for
Bottom.
the bottom one. Where? So notice I took this y equals and substituted in for the y.
Oh.
So I'm going to take this y equals and substitute that in for the y right there. That's going to give me an x, z, and z type of equation. So negative 5 times that y, which is 5x plus z minus 4, Then the rest of it is negative z equals 25. Let's do some distributing. That is negative 25x. That is a negative 5z. That is a plus 20 minus z equals 25. Let's combine our like terms. I have a negative 25x. With the z's, I have a negative 6z. And I'm going to move this 20 over. That's going to give me 5. So subtract 20 on both sides. 25 minus 20 is 5. This is going to give me my second equation that involves just an x and a z. So here are my two pairs. 2 by 2. How do we solve? Well, our goal here is to get this, we saw two methods yesterday. Substitution, right? I can plug this x into this x. What's another way you can solve a 2 by 2? That is now two-dimensional. Graphing. Very good. Well, let's look at a graph. Because I'm going to take some shortcuts. Just to remind you how important graphing can be and how quickly it can be.
Yes, no.
So my first equation, x equals negative 4. I'm going to just, for the sake of graphing, change that to a y. And then I have negative 25x minus 6y. I know it's a z, but I'm changing it now for the graph. Equals 5. And I see my solution is where? 1 and negative 5. So via graphing, actually I'll go over here and say graph. That gives me the solution of 1 and negative 5. Now note, this is my x, and this is my z, because that's what the equation involves. How is that going to help me find the y? Plug it in. So I get y equals 5 times x, which is 1, plus z, which is negative 5, minus 4. Take care of that for now. And negative 4. So that's y equals 5 minus 5 minus 4. Therefore, y equals, that's 0, negative 4. So how about that? That saved me a lot of work. Once I got to the 2 by 2, I simply just graphed it to find my x and z. That gives me 2 of my variables. Plug those in and gives me my last remaining variable. So my solution is 1, negative 4, and negative 5. Bam. You can test by plugging it in to each of the problems. So negative 5 times negative 4 is 20. 20 minus a negative 5 is 25. Hey, it worked out. Let's try the top one. Negative 4z, which is negative 5, so that's 20. 20 minus 19 is what? Worked out there. So you save yourself a lot of work by turning your 3 by 3 into a 2 by 2, graphing your results, and then using those coordinates to plug in to find out the variable. Yeah.
Can I go turn in my
Yeah.
wave?
So this graph is going to equal these coordinates here. One more. We're not going to solve this. I just want to make sure you know the steps in the process. What would be one of these equations you'll want to save?
Save?
Yeah, which is the first one that's you're going to use? Guaranteed you're going to use this one. Here I have x, y, and z. Here I have x, y, and z. Here I have just y and z.
Bottom?
The bottom one, yeah. Because remember, we want 2 by 2. So there's one with just 2 variables. Now I need an equation that's a y and a z. How can you pull that off?
Top one?
You're going to use the top one to do what?
Substitute, right?
Substitute it, yep. Substitute it into the other one, right there. If I plug that in, look how it gives me an equation that's z, y, and z. And another y.